Hi there, welcome to another episode on Netbooks, Video Learning. I'm Guy, and today's topic is Functions Part 1. Before we jump in, let's have a look at today's goals, based on the annual teaching plan. The annual teaching plan requires learners to comply with the learning outcomes for every topic. These learning outcomes will be tested in your exams. Let's have a look at the learning outcomes for this topic. You need to understand the form of a straight line function. This includes reflection of the function about the y-axis. We will cover the concepts in theory, then apply them to a question. You need to understand the form of a parabola. This includes reflection about the y-axis and application of the nature of roots to parabolas. We will go over everything you need to know, then apply what we've learned to a question. Let's start with the straight line function. You are already familiar with this function, in the form of y equals mx plus c. The straight line graph has two characteristics: the gradient and the y-intercept, represented by m and c respectively. Now, have a look at this new form, f of x equals ax plus q. Is this form any different to the one we're already familiar with? Not at all, we have simply changed the labels of the gradient and y-intercept. The gradient of a straight line graph is calculated as y2 minus y1 over x2 minus x1. Increasing the c, or q value, will shift the graph upward. Decreasing, will shift the graph downward. Now, let's introduce a new characteristic, the horizontal shift, denoted by p. Let's have a look at the effect of this characteristic graphically. Suppose we have a graph of y equals 2x plus 1. Let's see what happens if we introduce a p-value of positive 3. The graph is shifted 3 units to the left. So we see that, if we add to the x value, by making p positive, the graph shifts left. And subtracting will then cause the graph to shift to the right. Now, let's do some reflection. On reflection, reflecting about the x-axis will result in the y-coordinate changing signs. Let's look at a quick demonstration. We have 2, 3 becoming 2, negative 3. Graphically, we need to create a mirror image of the coordinate point across the x-axis. That means that the positive y distance from the x-axis must now become the mirrored distance in the negative direction. Now, let's move on to a reflection about the y-axis. Once again, a demonstration will help us understand this. When reflecting about the y-axis, the x-coordinate will change signs. We have 2, 3 becoming negative 2, 3. Graphically, we need to create a mirror image of the coordinate point across the y-axis. That means that the positive x distance from the y-axis must now become the mirrored distance in the negative direction. But you already knew all this. The question is, can we apply this reflection method to entire functions? Yes, we can. Let's take the example of y equals 2x plus 1. Suppose we want to reflect this about the y-axis. Well, to reflect about the y-axis, we know that the x value needs to change sign. So positive 2x will now become negative 2x. As easy as that. Let's dive into a question, to solidify everything we have covered so far. As always, we recommend that you do this in your book with us. We're given the equation of a straight line, with a missing a value and p value. We need to determine the equation of f, in this given form. This means we need to solve for a and p. Solving for a is straightforward, since we are given 2 points on the line, and we know that a is the gradient. We simply need to apply the gradient formula. We substitute the x and y values for the 2 points. You get a mark for substituting the points correctly into the gradient formula. We can solve for a, and we get a value of negative 2. This is worth a mark. We can substitute a back into the equation. Now, we just need to solve for the value of p. Well, if we substitute a point into the equation for x and y, we will have p as the only unknown in the equation. We will substitute the point negative 1, 2. Since we chose this point, why don't you try using the other point, to ensure that you get the same p value that we do. We multiply out the bracket, and solve for p. We get a p value of 1/2. The correct p value is worth a mark. Finally, we can substitute the value for p back into the equation, and we now have the equation of f fully defined. The final answer is worth a mark. We are now asked to determine the equation of g, which is the reflection of f, about the y-axis. We know that to reflect about the y-axis, we need to make the x value change signs. So wherever we had an x, in the original function of f, we will now have a negative x, in the function for g. Applying the correct reflection rule is worth a mark. Now, we were asked to get the function in the same form as f. So the x term can't have a coefficient. We need to take out the negative 1 from the bracket, to get rid of the coefficient of x. We simplify, and now have the equation for g of x. The final answer is worth a mark. Now, we're asked to describe the transformation to take f of x, to become h of x. If we list the two functions, we can see that only the p value, and q value, are different between the two. H of x is a half units further to the left. H of x is also 1 unit upward from f. So the transformation required is, translation half a unit to the left, and 1 unit upward. You get a mark for each translation correctly stated. Lastly, we're asked to sketch the graph. Let's remind ourselves of the function we're sketching. Now, ordinarily, we would need to solve for 2 points to plot. This would be done by selecting x values, and solving for their y values using the graph equation. But remember, we were already given 2 points. We plot our 2 points on the graph. Now, we draw a straight line through both our points. Lastly, we need to indicate any intercepts on our graph. Our x and y intercept is the origin. You get a mark for correctly plotting the points, for the correct drawing of the straight line, and for showing your intercept. We've now completed the first learning outcome for this video. Now, let's discuss the parabola. You're already familiar with the basic form of a parabola. Remember, a positive a value gives the parabola a smile, a negative a value gives the parabola a sad face. The q value, in this form, represents the y-intercept. This occurs at the turning point of the parabola. Let's introduce a new characteristic, the horizontal shift, represented by p. Note, if the graph shifts horizontally, q will no longer be the y-intercept. P, q will now be the turning point. Let's have a look at a demonstration of this. Let's consider the graph of y equals 2x squared, plus 1. If we introduce a p-value of 2, we see that the graph shifts to the right. As expected, based on the work we did earlier with the straight line graph, adding to x will cause the graph to shift left. And subtracting from x will cause the graph to shift right. Note the form of the equation we gave you as p being subtracted. Keep this in mind, when p is positive, we are subtracting from x, and when p is negative, we are adding to x. The axis of symmetry for a parabola is always going to be a vertical line, through the turning point. So the line x equals p. We do sometimes get a form given to us in tests or exams, with p as positive. In this case, the turning point will be at negative p, q. Now, if we multiply out the parabola in this turning point form, we will get the standard form. This looks familiar, doesn't it? It's our old faithful quadratic equation. When solving for the roots, or x-intercepts, of a parabola, we can use the quadratic formula if our parabola is in the standard form. We can also apply the nature of roots properties, since this is, in essence, just another quadratic equation. We covered the nature of roots in our algebra section. Let's do a quick recap. Let's discuss the nature of roots. This topic is about being able to predict the type of roots, or answers, a quadratic equation has. The prediction is based on the quadratic formula we discussed earlier. Looking at the formula, the special part of the formula is under the square root. This is the only part that can cause an error, since you can't have the square root of a negative number. This is also the only part which enables two separate answers, since we have plus or minus, for this square root. We call the part under the square root, the discriminant. If the discriminant is negative, we will have imaginary, or non-real roots. This is because we cannot take the square root of a negative number. If the discriminant is 0, well, the square root of 0 is 0. So we will have plus, or minus 0. Which means we won't really have two different answers. So we say that the roots will be real, and equal. If the discriminant is positive, then we have two real, and different roots. But, we have two categories for this. If the discriminant is a perfect square, then taking the square root will result in rational roots. If the discriminant is positive, but not a perfect square, then taking the square root will result in irrational roots. And that's the nature of roots. Now, let's apply everything we've covered on parabolas to a question. We're given the graph of a parabola with 2 points indicated, the turning point and y-intercept. We're asked to show that f of x is equal to x squared minus 4x minus 5. We need to solve for 3 unknowns, a, b, and c. But we are only given 2 points. Is this even possible? Yes, since one of those points is the turning point. Let's write down the turning point form of a parabola. We can substitute in the coordinates of the turning point in the place of p and q. Using the turning point form and correctly substituting is worth a mark. Now, if we substitute in the coordinates of the given point 0, -5, we will have a as the only unknown. We can solve for a, we get a value of 1. This is worth a mark. We substitute a back into the turning point form of the equation. We can multiply out the equation. If we collect like terms and simplify, we end up with a final equation of y equals x squared minus 4x minus 5. The final answer is worth a mark. Now, we're asked to determine the nature of the roots of f. We know that to determine the nature of roots, we need to evaluate the discriminant. We substitute the values for a, b, and c. We get a discriminant value of 36. Solving the discriminant is worth a mark. We have a positive discriminant, which is a perfect square. This means we will have real, rational, and unequal roots. The interpretation of the discriminant is worth a mark. We now need to determine the coordinates of e. E is the x-intercept. So we need to solve the roots of the parabola by letting y equal 0. We could have used the quadratic equation to solve for the roots at this stage. But we can just as easily factorize the trinomial. You get a mark for the factorization. You would have gotten a mark for correctly substituting in the quadratic equation if you went that route. We get 2 answers for x, -1 and 5. You get another mark for the correct answers. Now, which x value will represent e? Well, if we look at the graph, we can see that e is on the negative side of the x-axis. So the negative x value must be associated with e. We get the final coordinates for e as -1, 0. The final answer is worth a mark. Now, we're asked for the equation of the axis of symmetry. We know that the axis of symmetry, for a parabola, is a vertical line through the turning point. We get the equation as x equals 2. You get a mark for the final answer. We need to determine the region where the graph is negative. Looking at the graph, we can see this is between the 2 x-intercepts. So we know the region will definitely be between these 2 points. But, should we include the points themselves? The question says less than, or equal to 0? Not just less than 0. So yes, we include the intercepts. Remember, we already solved the values of the intercepts above. So we can write our region down as x, from -1 to +5, including the endpoints. You get a mark for correctly finding the 2 endpoints, and another mark for the notation. We now need to determine the equation of g, which is the reflection of f, about the y-axis, in the standard quadratic form. We know that for a reflection about the y-axis, we need to make x negative. Looking at the original function for f, there are 2 places we need to make x negative. Note that for the x squared position, only the x needs to become negative, not the whole power. So instead of x squared, we get -x all squared. Instead of -4 times x, we have -4 times -x. Correctly applying the transformation is worth a mark. Now, we multiply out everything and simplify to get g in the standard quadratic form. The final answer is worth a mark. Lastly, we need to determine the average gradient between the points d and a. Wait. Is it possible to find the gradient of a curve? The key word here is average. We need the average gradient between these 2 points. To find the average gradient, we pretend that we are working with a straight line, and use the gradient formula we all know and love. We substitute in the points. Correct substitution is worth a mark. We solve for the gradient, and get a value of -2. It makes sense that we got a negative, since the graph is decreasing between A and D. The final answer is worth a mark. We have now completed the last learning outcome for this video. Thanks for joining us on this episode, on Netbooks, Video Learning. Catch you next time, right here.